Welcome to video 1 of a 3-part series to help you walk through the midterm review packet. It should be noted that this review series is only meant as a guide, not as a solution set to all of the problems. Feel free to skip around the videos for the sections that you need help with only. Our first section brings us back to the beginning of the year to rotational symmetry. Now, keep in mind that we have two types of rotational symmetry. One just means, can you rotate that figure less than all the way around, less than 360 degrees, and still have an identical figure? Then we have this idea of point symmetry. Remember that point symmetry is strictly 180 degrees. So our first figure right here, is it possible to rotate this figure around and end up with that same figure? Of course, at 90 degrees you can, at 180 degrees you can, and at 270 degrees you can obtain the same figure. So it has rotational symmetry, and it says to circle it if it does. And then it also says to put a star next to anything that has point symmetry. So since this figure is the same upside down, I'm going to put a star. And remember that 180 degrees is the same as upside down. Be careful, right? Be careful with figures that certainly have some rotational symmetry, right? This figure right here, that star, can be moved around in a fashion where you have the identical star. But notice at the top it has one pointy piece, and at the bottom it has 2 points. So at upside down, I don't think that we have point symmetry on this one. This next section, we're going to talk about transformations. So if you follow down here, I have the 4 transformations that we discussed. Number 1 are reflections, right? You're going to flip across the x-axis, the y-axis, right? The x or the y-axis, or maybe just a vertical line or a horizontal line. On the rotation side of things, we're going to spin around a fixed point, right? That's going to change its orientation and location, just like a reflection would. Translation is going to change its location, but not its orientation. We're going to just slide it. So if it's right side up, it's still going to be right side up after we slide it. Now these 3, right, are known as rigid transformations. Right, so we got rigid, right, doesn't change size, it stays rigid. Transformation, right, so a rigid transformation changes orientation, it might change location, right, it might be upside down, but it doesn't change size. Dilations are not, right, they are not rigid transformations. Why? Because they shrink or enlarge the shape. They do change size, right? So that's why I wrote dilation in white. So 1 through 3 are rigid transformations. Number 4, right? Number 4 is not a rigid transformation. Now let's take a look up at, say, this example right here. Well, first and foremost, is this a dilation? No, it doesn't change size, right? It doesn't change size, so it's not a dilation. Is it a reflection? Does this shape flip over upside down to get there? No, it's not a reflection. So we're going to cross off reflection. And what about a translation? Well, it changes its orientation, so it can't be a translation because it's not right side up the same way it was at the top piece or the bottom piece. And then that really just leaves us with rotation. So here we go. We're going to fill in a rotation for that one. Also worthy to notice that we started from A to A prime. So A goes to A prime. Remember that this is called our pre-image, and A prime is going to be called our image. Next sections, we're looking for you to identify still what type of transformation is this. So it's the same size, so it's not a dilation, but it doesn't look like it's a reflection. It doesn't look like it's a translation. It's not sliding anywhere. It definitely changes orientation. So it looks like this is a rotation. And it looks like the fixed point here was about the origin. And remember, if you had your patty paper, that you could trace this and then sort of spin this around. sort of as such. It's not as smooth as the patty paper, and it looks like that rotated around the origin. So it's definitely a rotation, and it's definitely spinning in the counterclockwise direction, right? And so counterclockwise is the default way that we rotate. So this is a counterclockwise rotation. Now we have some rules, and these rules will be on your formula card for the midterm. You won't have to memorize this particular set. Now, the mapping rules for rotations only are the rules that you will have. Your other mapping rules, you'll need to iron that out on the fly during the exam, but those are pretty easy, and this is how you do it on your own. If you take a look, A was at 1, 7, and A prime's at negative 7, 1. So if 1, 7 mapped to negative 7, 1, then what happened x, y, y's? The x's and y's obviously switched. Y went over to the x. Y was originally positive, now it's negative. So I'll say that we went to the opposite of y, and then the x went to the y vert value, and it stayed the same sign, so x just stays x. So it's not so much that y went from a positive to a negative, and so just because it became negative doesn't mean that that's negative. It went to a different sign. So what I mean is if you started off at negative and then it went to positive, I would still say that y went to the opposite of y. So there's our answer. Now, again, in the mapping rules, we'll say that x, y goes to negative y, x. And for your 180-degree rule, x goes to the opposite of x and opposite of y. And for 270, x goes to y, and y goes to the opposite of x. So you'll notice that the 90 and the 270 are very similar. You don't want to get the signs messed up. But most importantly, just pay attention to the coordinates, right? We gave you the grid values right here, so try to iron that out on your own. All right, moving forward. So some of the other ones that you'll have is a reflection and a translation, but here we have the changing of the size. So obviously this is a dilation. And with a dilation, you'll need to give your K factor. And what that is what value of K, this multiplier, makes A go to A prime. So first, find your coordinates for A. So A was at 0, 3, and A prime is at 0, 9. So what value of K do you multiply 3 by? So 3 times K is equal to 9. Divide by 3, K is equal to 3. So we'll write that as a rule as 3x, 3y. That's what turns all of these values to go to the image. For instance, 2, 1 went to B prime, 6, 3. If you take 2 times 3, you get 6, and if you take 1 times 3, you get 3. So it looks like that K value equal to 3 sends us from B to B prime. So that everything checks out there. And it might be helpful to just say, oh, by the way, this is an enlargement. That reminds us that the K factor is greater than 1. Okay, next. Our next section, we have double transformation. So we're applying a transformation twice. So we have this threefold package to do over here. First, we're going to reflect across the line AB. So here's line AB. So we're going to count units. That's 1 unit. So E prime lands here. 1, 2, 3. 1, 2, 3. F prime lands here. So we'll say that's E prime, F prime. G prime is 1, 2, 3, 4. So 1, 2, 3, 4. Here's G prime. And H prime is 1. So unit away. So we got our H prime. Now we're going to connect the dots and redraw our figure. And so what do we have here? We have a mirror image of the original pre-image, right? So here's our pre-image. And then here's our first image. Now, we move on to part B. It says reflect our new piece over line CD. So now this figure here is going to become our new pre-image, and we'll land up with a new reflection over here. Now I'm just going to do E prime and F prime. So we're going to count again, hops. So this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Looks like that's going to be our E double prime. And F double prime is 1, 2, 3 away on this side. So 1, 2, 3 away on that side. And that's going to be our F double prime. And now we're going to want to connect the dots. Now, as you complete this and you get your G double prime and H double prime, you should have a figure in the same orientation as our original figure was over here. You're going to end up with an EFGH double prime figure. And the last question asks, well, what single transformation? How could we have just taken this shape here and moved it over to this location in one fell swoop? Well, obviously, we reflected it twice, but to keep that same orientation, a translation, right, sliding it would have worked, right? So we could have taken this figure and slid it right across over here. So I would say, well, a translation would do that. But I need to specify a direction. So I would probably say something like translation to the right and the number of units. Now, what you should remember is that that number of units, that magical number of units, is the double value of the distance between the two reflecting lines. So we reflect over this line, reflect over this line. They are 1, 2, 3, 4, 5, 6 units away. Now let's see how far it takes to go from E all the way to E double prime. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 6 units, and that whole distance across was 12 units. Coincidentally, 6 times 2 gives us 12. So a translation of twice the distance between the two reflected lines is the number of units. So a translation to the right, 12 units, or a little more slick way to write it is 12 units right, 0 units up or down, and we could write this in vector notation. Remember vector notation? So again, verbally explaining it, translation, write 12 units, or in vector notation, that one little vector notation says everything that I said in words there. And that's our last piece. So that's a whole lot of scribble there, but you should have 3 different pictures, right? 3 different complete pictures, all of your prime labeled points, and a final answer for part C. Hopefully that was helpful. In our next double transformation, we're going to be talking about reflecting over this line and then reflecting over this line. So at this end result, how do you go from here all the way to there? Well, that arcing motion obviously is a rotation. And keep in mind that that rotational answer is always going to be, well, if we're going this way, we're going counterclockwise. Right? So we're going counterclockwise, be a rotation, and it always ends up being double the original angle that was formed between A prime, B, and A. A prime, B, and A is right here. So what we're talking about is if this angle is 45 degrees, the rotation to move this figure from here over to there is going to be twice 45 degrees. It's going to be 90 degrees. So just kind of gave you a little sneak peek on the part C. But now how do we actually move the figure that way in a reasonably smooth fashion? Okay, let's take this a step at a time. I'm going to clean up the board here first. The first thing that we're going to do is we're going to reflect across AB. So we just move at a 90-degree straight line fashion over that line. So we're just going to count boxes like we did in the last problem, but we're counting diagonally. So this is one full box. So C prime is going to land right there. D prime is 1, 2 and a half. So here's our other half, 1, 2. There's our d prime. And E is 1.5. There's our half, and there's the 1. That's E prime, and now we're just going to connect the dots. So I've just neatened up my picture so that's not confusing for you to follow, but using a straight edge is a good idea as well. All right, and now we're going to reflect across line BA prime. So here's B and A prime, so we're talking about this line right here. So now we're just counting horizontal boxes, so 1, 2, 1, 2, E double prime, 1, 2, 3, 4, 1, 2, 3, 4. That's our C double prime. And D, 1, 2, 3, 4, 1, 2, 3, 4. We got our D double prime. Connect the dots and make sure that you have a rigid transformation, right? Same shape, just different orientation and location. Now I've set up the shape so that I can rotate this around and stop it right in just the right spot. And I'm just going to drag this over here. And it looks like that's a reasonable size. I know it's not directly over the top of it, but enough to say that, yeah, if we rotate this around, it looks like that double reflection was a rotation. And as we said earlier, that a rotation of 90 degrees, which was 45 times 2, gets us that last answer there. So what's single transformation? A rotation counterclockwise of 90 degrees. And we got that 90 because it's always going to be double the angle formed right here. On this next question, we're going to talk about perimeter of the quadrilateral. And so now we're going to be engaged in the distance formula. So we got x sub 2 minus x sub 1 all squared plus y sub 2 minus y sub 1 all squared. That's our distance formula, and you should be pretty well versed with this by now. While we're here, let's keep in mind that our slope formula is going to be the difference of the y values over the distance, the difference of the x values. That's our slope. And to keep in mind, lines are perpendicular if slope 1 times slope 2 equals -1. So that's the definition of being perpendicular. And that should handle all the questions that are going to come at us. So first and foremost, you can just count the distance here. That's 3 units. And you can just count the distance here. That's 3 units. Now for the distance between D and C, we're going to have to use the distance formula. And it looks like D is at 4, 9. And it looks like C is at 7, 2. So you can go ahead and process those two in the distance formula. The other option you can have is to create a right triangle and say, hey, this is a distance of 3. 1, 2, 3, 4, 5, 6, 7, right, is the distance over here. And you could say that there's a right angle here. That's our hypotenuse. So 7 squared plus 3 squared is equal to the distance squared there. And I would want the actual answer. So D is going to be the square root of 49 plus 9. Either way, that's the answer you're going to deal with when you use the distance formula or when you create that right triangle. So for B to C, you can create the right triangle there as well. And you can count this distance and apply the Pythagorean theorem. Now what are you going to do? You're going to have these 4 lengths. And what are you going to do with those 4 lengths? You're going to add them all together. And once you add all 4 answers, you should have the answer for the perimeter of the quadrilateral. As far as a line of symmetry, we're going to talk about maybe a line from A to C. Now technically, this actually is not the answer. Line segment AC is not a line of symmetry because this technically isn't a kite. So technically, those 2 triangles formed by that line aren't totally identical, but we're just kind of looking to see if you have an idea of where the limit symmetry might be if there was one. So it's kind of a tricky thing. Moving on to whether or not there are any lines that are perpendicular or slopes. Now for these slopes, we've guided you, the slope of BD, right? Talking about the slope of that line. Well, D is again at 4, 9, and B is at 1, 6. So we're going to process our slope formula. So what do we have here? the difference of the y values, 9 minus 6, and the difference of the x values in the same fashion. So if I start with 9, I got to start with 4. And so this is our slope of BD is going to be equal to 3 over 3, which is equal to 1. Now, process the slope for AC. So in the same fashion, what is the slope of that line? C is at 7, 2, and A is at 1, 9. So you can process that and get an answer. Take these two answers and multiply them. Does 1 times whatever this is equal -1? If it does, then we would say yes, they are perpendicular. If not, then we would say no. So either they are or they are not, because the products do or don't equal -1, right? The products of those two slopes either do equal -1, in which case I would say they are, or they don't equal -1, in which case I would say they're not. And that's how you complete that problem. On that last question, I talked about, this concept of a line of symmetry. A line of symmetry should divide that object into two identical halves. So there is a horizontal line of symmetry on this little sort of crescent-looking shape, right? And so this top piece would fold over very nicely onto the bottom piece. So there's one line of symmetry there. So on that last problem, because it is not a kite, it doesn't actually have identical pieces, but that, again, that line that I had thrown in as a possible answer is a reasonable approximation to a line of symmetry. So right here, you're going to sketch any lines. So for this square here, it's tilted to the side a little bit, but there's one to get you going. There's several more, right? There's more than one more line of symmetry there. Some of these don't have any lines of symmetry, and if there's no line of symmetry on the figure itself, just write the word none, and that's that. The last section of Unit 1 review, which is probably the largest review section, we're talking about a builder building diagonal braces. So where are these diagonal braces? They're here and they are here, right? Diagonal braces give strength to a rectangle. A rectangle or a square is not really a very strong geometric structure in real life, and so we add in some triangular pieces. Right? Triangles are very strong geometric figures in real life. And so what we're looking for is the length of these diagonals. Well, if you take a look then, you should be able to see that you have a right triangle here, of which you know one leg and the other leg, and I guess this would be the right angle, so we're staring at the hypotenuse over there. It looks like you're looking for the hypotenuse, and just keep in mind that a squared plus b squared equals c squared. Okay, same scenario here. Got an obvious right triangle sitting here with the right angle there. That's the hypotenuse. And I guess I don't know that piece, but the key question is, what was the original height of the post, right? The post was broken. That's what this diagram's showing. So we have 2 feet here and 18 inches. Keep in mind that 1 foot equals 12 inches. So 2 feet, of course, equals 24 inches. And then I think it's best if you work in inches for the whole problem. You're going to end up finding this length, and we want to know is how tall was it originally, right? That's your final answer. So don't just put the answer of the Pythagorean theorem, you have to answer the actual question. All right, that's the end of Unit 1 review.